In this video, I'll try to answer the question for you, why do we have leap years? What are the rules for leap year? And what are the consequences of our calendar system? So I hope you pause the video when you feel that you need a little extra information. But just to remind you, a long time ago, when you were a child, December, January, and February were the winter months in the Northern Hemisphere. When you're going to be older, many years from now, the seasons will still occur in the same months. December, January, and February will still be winter. Our calendar does keep in sync with the seasons. Well, you might ask, why do we have seasons? So the Earth is spinning on its axis, 24 hours roughly for a day, and the rotation axis of the Earth is not perpendicular to the plane of the orbit. That's important. The rotation axis tilts by 23 degrees. That causes the seasons. The Earth orbits the Sun. The rotation axis approximately remains pointed to the same location on the sky during our orbit. So in this diagram, we have winter for the Northern Hemisphere. Winter is being shown here. The Sun being off to the left here. Here's the orbital plane of the Earth, and we're finding the Sun below what we'd call the celestial equator. A lot of terms here. You may need to pause the video. The Earth has an equator. It runs along here in this diagram. Above the Earth's equator on the sky, we have the celestial equator. And in this slide, the Sun is below the celestial equator. For an observer in the Northern Hemisphere, the Sun will be low in the sky. It will be low in the sky. Another diagram here showing sunlight coming onto the Earth. Again, winter in the Northern Hemisphere. And the Sun being low in the sky, it doesn't stay above the horizon very long. And we have the sunlight not directly beaming down on the surface of the Earth. The energy of the sunlight is spread over a larger area on the Earth compared to down in the Southern Hemisphere now that's having their summer. The sunlight hits more directly. Well, here's the year. Here's the year. And the rotation axis, as you can see, is remaining pointed towards the same star out on the sky. Here's our winter for the Northern Hemisphere. The Earth is tilted away from the Sun for an observer in the Northern Hemisphere. And the sunlight, again, not hitting directly. We get cooler temperatures. However, I would remind you, the Earth is actually closest to the Sun in January. The Earth's orbit is elliptical, slightly elliptical. And the tilt of the Earth causes the seasons, has this effect of the Sun being above the horizon a different number of hours, short number of hours above the horizon in the winter, long number of hours above the horizon in summertime for a hemisphere, and the sunlight is spread out, less direct on the ground, so each square meter does not receive as much energy when that hemisphere is having its winter. In between these times of summer and winter, we have the equinox times, when we have 12 hours for the Sun above the horizon for every place on the Earth. The Sun is above the Earth's equator. For an observer standing on the Earth's equator, the Sun would be directly overhead. So again, a lot to absorb in these diagrams. Feel free to pause the video and inspect them a little more closely. Here's the wording of what I just said, and I'm not going to repeat all of this, but for the Northern Hemisphere, summertime is when the Earth is tilted towards the Sun. If I just go back, if I can here. So summertime, the Earth is tilted towards the Sun. This does not bring us closer to the Sun by any appreciable amount. This drawing is not to scale. The Sun should be much smaller. The Earth should be much smaller. In wintertime, Northern Hemisphere is tilted away from the Sun. And again, to emphasize, it's the tilt of the Earth that causes the seasons. It's not the Earth's orbit and Earth being closer or further away from the sun. The Earth's orbit is almost a circle. So what is a year? Just roughly time to go around the sun, right? Well, we need a little bit more detail about this. I'm going to talk about vernal equinox. Vernal equinox. As we observe the sun on the sky, there is a time of the year when the sun is right above the Earth's equator, and for an observer in the northern hemisphere, we're seeing the sun move from the south towards the north on the sky. And this occurs in March currently with our calendar, and it's the vernal equinox, what we call the start of spring for the northern hemisphere. Well, we can be a little bit more specific than about year. A tropical year, a year related to the seasons, a tropical year. This is the length of time between two successive vernal equinoxes, from spring to spring, if you will, for the northern hemisphere. And our calendar is built to keep track of this tropical year. I'm not going to talk about the sidereal year, but it's another definition you might want to research on your own. So the calendar, before 46 BC, some cultures did use calendars, but for the most part, they had 365 days in their year, and they did not stay in sync with the seasons. So the scientists, if you will, in the time of Julius Caesar knew that it takes the sun 365.25 days to repeat its position on the sky, from one vernal equinox to the next vernal equinox. They didn't know this exactly, but they knew it was not 365. So if you build a calendar that only has 365 days, after 4 years, the calendar is going to be out of sync with the tropical year by 1 day, out of sync with the sun's location on the sky by 1 day. Well, that's not much. That's just 1 day. Our weather is so variable. How could we notice the calendar being out of sync with our seasons by 1 day? We couldn't. But 100 years. So 4 years, 1 day. There are 25 4-year periods in 100 years. So our calendar would be out of sync with the seasons by 25 days a month. Now you're going to start to notice that. And after 700 years, the calendar would be out of sync by 175 days. I've just multiplied 25 by 7. 100 years here, 700 years here. And now we would have June, July, and August as our winter months. So 700 years, you definitely know the difference. One person wouldn't. They don't live that long. The person doesn't live that long, but the calendar would no longer be in sync. So how can this be fixed? Well, the Julian calendar, 46 BC, they came up with a system. For 3 years in a row, the year has 365 days. Then on the next year, the 4th year in the cycle, 366 days, leap year, and we have 29 days in February instead of 28, a leap day. This extra day does keep the calendar in sync with the seasons as long as the tropical year is exactly 365.25 days. There's more information on this. There's a long website address. To get to this, do a little Google search. Type the word site, S-I-T-E, :nasa.gov, no spaces in here. That will command Google to search nasa.gov and make it search for calendar calculations. So here we go. I'd like you to read this a little bit. There is a problem. The tropical year is not exactly 365.25 days. It's closer to 365.2422, and even this is not exact. So let's consider what's going to happen here. 4 tropical years, that would be 1,460.9688 days. The Julian calendar is going to deliver to us 1,461 days. Close, but not exact. After 4 years, the calendar is a little bit out of sync with the seasons, but only by 0.0312 days. Well, who cares about that? Well, in the year 1500, people started to care. A little bit beyond 1500, but I did this calculation for 1500. What's the error after 1,500 years of the Julian calendar system? Well, if I divide 1,500 by 4 and then multiply by the error we have over the 4-year cycle, I come up with 12 days. And now people were noticing that the calendar was getting out of sync with the seasons. So come up with new rules for leap year. The Julian calendar has too many days, too many leap years that give us the extra day in the calendar system. So the Gregorian calendar was proposed, and October 1582, they made a sudden shift. It didn't make a lot of people happy. They just cut out 10 days from October. England, in fact, didn't like this, such that they put off this inevitable decision to change the leap year rule until 1752. But October 1582, we get the Gregorian calendar established. It has new rules here. So yeah, we're going to have leap years when a year is divisible by 4, almost always. If we're on a century year, 1700, 1800, 1900, and that century year is not evenly divisible by 400, then this year is not a leap year. The 1700 is not a leap year. If the year is evenly divisible by 400, then it is a leap year. So the year 2000 that you may have enjoyed was a leap year. So this is the Gregorian calendar, a slight change from the Julian calendar. It takes out 3 leap years. It takes out 3 leap years out of every 400 that would have been in the Julian calendar. And this makes it better. The Julian calendar is better at keeping in sync with the seasons. However, it's not perfect. If you work out the average number of days, and I didn't actually work it out, I just took it from this website, the average number of days for a year in the Gregorian system is 365.2425 days, with all the century year business being accounted for. The correct number, the more correct number, is 365.24219, and there is some variability here at this last digit. You can read about it at this website, and I'll put these websites in the description of the video. So we have a difference here of 0.00031 days every year on average. The Gregorian calendar is not correctly keeping track of the seasons. I worked this out, so after 3,226 years, the error would be 1 day. There's another effect going on here. So the Gregorian calendar is fine. Every 3,000 years, roughly, you're out of sync by 1 day. It's not a big deal. Nobody's going to revise the calendar in your lifetime to account for that. There's another effect. The rotation axis of the Earth does not always point to the same spot on the sky. There's an effect called precession. I'm not going to go into the details of that. Do a Google search, or maybe I'll make another video. So what's the effect of precession? Well, it turns out the location where the sun is on the celestial equator in March, that slowly is shifting around the sky. The Earth is spinning like a top, and it's not stable in its spin direction. Just like when a top first starts, it's pretty stable where the rotation axis points, but as it slows down, it wobbles more and more. The Earth is wobbling, and we're not in danger of tipping over. That's another video that the moon has a role to play there. We're not going to go into that. But the rotation axis of the Earth does move around the sky. 26,000 years to go completely around. So when the sun is on the celestial equator at this time of the vernal equinox, the sun is, quote unquote, in a certain constellation, lined up with a certain constellation as viewed from Earth. That constellation changes because of precession. About every 2,000 years, the vernal equinox location is in a different constellation. Currently, Orion is a nice constellation, and it's in the winter sky. It's in the winter season. However, in 13,000 years, because of precession, our calendar will still keep us lined up with the seasons. Spring will occur, in April and May, but Orion will be visible in the summer nights, instead of in the winter nights. So just a little food for thought there. So, conclusion, why do we have leap years? To keep our calendars synchronized with our seasons. The rules for determining a leap year were first developed 46 BC and then revised to better keep us in sync in 1582 AD. If you want to view some other videos, a couple of websites you could go to that list all the videos. This is all free. There's no registration. You do not give me any information. I don't put cookies on your browser. I don't ask for donations. But you can look at my videos for physics and astronomy, .gpclements.com, and get some information there. If you like my YouTube videos, please subscribe and let others know about this resource. Hope you enjoyed.